Hello, good evening.
Yes, sir.
Yes, sir. Just tell me the last topic what we did in last class.
Sir, state of function.
State of function.
Yes, sir. Internal energy.
So I think the last part would be work done, calculation of work done.
Yes, sir.
Okay. Next is thermodynamical process. First is isobaric process. Iso means same, bar defines U for pressure. So we'll say the pressure which is carried out at constant pressure is called isobaric process. It is also called Charles' law. So we can define this part as the process which is carried out at constant pressure. According to ideal gas equation, PV is equals to nRT. If pressure is constant, then you're left with volume and temperature directly proportional to each other, since n number of moles and R being constant. So we can say at constant pressure, volume and temperature will be directly proportional to each other. So in this part, pressure is constant, volume is directly proportional to temperature. So we can write according to this equation, V1 by T1 is equals to V2 by T2 as equation of state. Harsh, is it clear?
Yes, sir. Yes, sir.
Next, to define general expression, P V to the power x is equals to constant. So what should be the value of x so that P becomes constant? So you will say, put x to be 0. So if you put x is equals to 0 in this part, V to the power 0 will become 1. So you're left with P is equals to constant. So we can say x in this part should be equals to 0. So related to this part, we can define molar specific heat constant at constant pressure. So what was the general expression for calculating molar specific heat? Harsh?
Yes, sir.
Tell me the general expression of molar specific heat.
The general expression of molar specific heat. C.
I defined you in last class. C is equals to R
R
divided
by
by gamma
R
minus 1.
minus 1.
R by x minus 1. So we have to put in this expression x to be 0. Okay?
Yes, sir.
According to this relation. So if you put x to be 0 in this part, so you'll get this minus 1 and this minus plus. So you're left with R by gamma minus 1 plus R. So on simplifying it, you will get gamma times R divided by gamma minus 1. In terms of degree of freedom, it will be equals to 1 plus F by 2 multiplied by R. And since this particular molar specific heat is at constant pressure, so we may write it as Cp. It means molar specific heat at constant pressure. Is it clear?
Yes, sir.
Next, we have to plot a variation of pressure versus volume, pressure versus temperature, and volume versus temperature, which is also called indicator diagram. So in this part, we have constant pressure. So at constant pressure, graph will be like this. Similarly, for temperature, it will be this. And for volume, it will be straight line from origin like this. So this is pressure versus volume graph, pressure versus temperature graph, and volume versus temperature graph. In first part, we have constant pressure. So only volume will change from one point to another. I'm just considering expansion of gas. So volume would increase from some initial value to some final value. This graph is also called indicator diagram. Next, for pressure versus temperature, since pressure is constant, so volume and temperature will be directly proportional to each other. So again, temperature will be increasing from some initial value to some final value. In third part, according to ideal gas equation, PV is equals to nRT.
nRT.
So in this part, volume and temperature is directly proportional to each other, or simply you can say volume is in perpendicular side and temperature is along base side. So we can write it as volume divided by temperature, nR divided by P. Now, in this expression, we have this part, which is related with pressure like this. This quantity is nothing but ratio of perpendicular by base. So we can write it as slope of volume versus temperature. And it is relating with pressure as inversely. So we can say graph or slope of volume versus temperature graph will be inversely proportional to pressure. So greater the slope of the curve, it will have lesser pressure. Is it clear?
Yes, sir.
First, write it down till this part.
So,
Yes.
no, sir, there was some blue block that is blocking the view. Sir.
Yes, Harsh.
No, sir, there was some blue thing that was blocking the screen. So I just told you.
Oh, just 1 minute.
Done, sir.
Now we have to calculate related term only for PV graph. Let me define you first. There will be question. Let's say this is A and this is B, pressure, volume versus temperature. So you will be asked to define relation between pressure for A and B. Define the relation between PA and PB. Yes, Harsh, just tell me.
Relation between P A and PB.
Just say we have volume versus temperature graph. In
Yes.
this last part, I defined you slope of volume versus temperature curve will be inversely proportional to pressure. Is it clear?
Yes, sir.
So first we have to calculate slope related to these two different curves. So for A, it will be from this point to this point, but for B, it will be from this point to this point. Which curve is more having more inclination with the x-axis, A or B?
PB, sir.
Good. So we can say greater the slope of the curve, it will have smaller pressure. It means
Okay.
PB is smaller as compared to PA.
PA.
Since slope of
Curve
volume
has higher
versus
inclination.
temperature graph will be inversely proportional to pressure.
Pressure.
That's why.
Okay.
Next, we have to define work done. So in last class, I had defined you how to calculate work done in a particular process. Just 1 minute for PV diagram or for PV graph. This is PV curve, which is parallel to x-axis.
Yes,
so
sir.
what will be its inclination with respect to x-axis?
0.
Good. So if you have to calculate slope of PV graph, that is dP by dV, so it will be tan 0, that is 0. So using this part, we may find bulk modulus. Let me define you the formula related to the slope to calculate bulk modulus. As we had, bulk modulus is equals to volumetric stress by volumetric strain. In mechanical properties of solid, I define you.
Yes, sir.
So we can say
Volumetric stress by
volumetric
strain.
stress is simply pressure applied, while volumetric strain is delta V by V. So we may write it as delta P divided by delta V with volume and with negative sign since volume of body will be decreasing. Now, if you have to take this particular part to be instantaneous, so it will become minus of derivative of P with respect to volume times volume is equals to pressure. Is it clear?
Yes, sir.
So we can say bulk modulus is equals to minus of dP by dV multiplied by V. And dP by dV we have 0, so it will become 0. It means there will be no elasticity for this process, that is isobaric process.
Okay, sir.
Just write it down.
So, like in my school, we just studied this definition. We didn't do anything of this graphs and all.
Okay.
Yeah. Like after this, we started specific heat capacity, Mayer's relation,
Okay. They have
and
just
then
defined you. They have just defined you Cp and Cv and relationship between them. Pi Cp is greater than Cv. These things only.
yeah, that's it.
Okay.
And then the difference between extensive and intensive thermodynamics variable. That's it, sir. That's it.
Know any work done in isothermal process?
Work done in isothermal process.
Yeah.
So they have just no, so that's just isothermal process, isochronic. They have just given the
Definition part.
definition part, and for isobaric they have written dq is equal to du plus dw. That's it. The equation.
So in your final exam, there will be no questions related to those different terms.
No, sir, because this chapter is over for us, and we have models next week.
Okay. When is the final exam?
Final is 17th March.
Okay. So should I skip this all?
Yeah, and this they skipped 2 chapters also. They didn't do it. They'll
Which
do it
one?
afterwards. It's oscillation.
And waves.
Yeah, and the last one, which was it? I forgot the name.
Waves.
Yeah, waves, oscillation waves. Yes, sir. That's it.
Okay.
And then they will give these 2 chapters in the final exams. That's it.
Okay. So we should. So what will you do now? Should we skip this?
No, sir. We'll do this question and then we'll see.
Okay. You may just write it down. Then I'm
Yes,
just
sir.
defining the main part only. Okay.
Yeah.
So in which chapter you are in school?
Sir, last week we started oscillations, but then exams are coming, so we started revision
Okay.
because it's not coming in models, it's coming in finals, so they have time.
When is the model exam?
Sir, next week, 20th Feb.
Okay.
And first exam is physics.
So it will start on 28th and then it will end on,
And
I
at
think,
3rd March, yes, sir, 3rd March.
Then again, your syllabus will resume from oscillation and waves.
Yeah, again.
Okay.
Done, sir.
Okay.
Sir, when will we finish the portion?
Yes.
When will we finish the portion?
This part or the entire syllabus?
Like this chapter and yeah, okay, in entire syllabus, yes.
I think it will be in this month. I think, inshallah.
Okay, this month and sir,
At the end of this.
I don't think I can do classes in this like after 20th Feb. Like in this month, March I can do. Like till 3rd March, I can't do. I don't think because I have exams.
Okay, so
Then again, like it's only 2 weeks till 17th. Like 4
okay,
classes.
Okay, we will finish till that. Okay.
Yes, sir. Done, sir.
Okay. Next, if you have to calculate work done in this process or work done in any process, it will be simply area under pressure volume graph. Okay, and nothing more. Instead of defining all different process, let me summarize you all different terms. So it will become easy for you. Then I will define you the Mayer's relation. You haven't done heat engine, refrigerator, heat pump, these things?
No, sir. The only thing related to heat was there in thermodynamics was specific heat capacity.
Okay. First was isobaric. Second is isochoric. Third is isothermal.
Yes, sir.
Fourth is adiabatic.
Adiabatic.
So using equation of state, using general equation of ideal gas, PV is equals to nRT. In first part, pressure will be constant.
Yes, sir.
So volume and temperature will be directly proportional to each other. In second part, volume is constant.
So temperature is inversely proportional.
Pressure and temperature will be directly proportional to each other.
Yeah, directly proportional.
In third part, isothermal. Temperature
is constant.
So pressure and volume will be inversely proportional to each other. In adiabatic part, Q or delta Q is equals to 0 or simply Q is equals to constant. So in this part, we can say first expression will be PV to the power gamma is equals to constant. Yes. You may convert any of these terms by using ideal gas equation to transform into next other term or equation of state in some other term also. So these are some different process. Next, for each different process, we have to define work done, internal energy, and heat supply. In first part, if pressure is constant, so work done will be simply P, since pressure is constant, volume final minus volume initial. Using first law, you can say dq is equals to du plus dw. So you may find any one of variable term by using this law. Next, we can define next process, that is molar specific heat for isobaric process, that is CP. I will define you later. For isochoric process, since there is no change in volume, so work done will be 0. So according to first law, dq will equals to du in this part. Next, for isothermal, temperature is constant. So change in internal energy will be 0. So amount of heat supplied or rejected must equals to simply work done, which is equals to nRT ln V final by V initial. That is log final by log initial. For adiabatic part, dq is equals to 0. So according to first law, you'll say du plus dw will equals to 0, and work done will be equals to just minus of internal energy. Is it clear?
Yes, sir.
So these are different process and these are different terms you will be asked to calculate. First, write it down this different part. So when will 12th start in his school?
So, yes, sir. April 10th.
Okay.
Sir, is 12th easier than 11th?
Yeah. Only first 4 chapters is too much lengthy. Rest the entire syllabus is equals to just 4 chapter of the first 4 part.
Okay. Done, sir.
You have done fusion term or calculation of internal energy for fusion, calculation of internal energy for vaporization. These things.
So, 1 minute. Let's check.
So what they will
Sir,
ask you just to explain these different process.
I don't know, sir. It's just written and they'll say, because they won't ask the formulas like inside this.
Okay, let me just define you some more different term.
After this, it's written like Kelvin's plane statement and
That is second
process.
law statement. Okay,
Yeah.
let me define you some term. If suppose if you have to define melting point and similarly if you have to define boiling point. So melting is the temperature at which solid start melting.
Melting into
So
liquid.
for ice, it will be 0 degrees Celsius
Yes.
and at constant pressure that is 1 atm. Suppose if we have to calculate internal energy during these different processes, so we may write it as for fusion and for vaporization. So for fusion, we may write according to first law, dq is equals to du plus dw. I define you for fusion, that is heat required to change its state. So it will be latent heat of fusion. So it will be mass of substance times latent heat of fusion constant is equals to change in internal energy we can calculate, and work done is simply pressure times change in volume, that is V final minus V initial. And this pressure will be equals to just 1 atm. Is it clear?
Yes, sir.
Similarly, according to vaporization, using first law, we can say dq is equals to du plus dw. dq in this case will be mass times latent vaporization constant. Du we have to calculate, and work done is pressure times change in volume, that is V final minus V initial. Let me give you some question related to this part. You will be asked, if 0.1 gram ice at 0 degrees Celsius melts into water so that volume changes by 10 centimeter cube. Find change in internal energy. So in this part, we have mass of ice. So
Yes,
we
sir.
can say, according to fusion formula, we can say mass of ice
Mass
times
of
latent fusion constant is equals to dq
du plus
plus p times dv in
dv.
case of work done. So mass of ice, we have 0.1 gram, and latent fusion constant is 80 calorie
Eight.
per gram. So this entire term will be in calorie. How to convert this into joule? Just multiply it by 4.2. Is it
Okay.
clear?
Yes, sir.
As 1 calorie is equals to 4.2 joule. That's why. So it will be equals to change in internal energy. We have to calculate pressure is 1 atm, that is 1 into the power 5 Pascal, multiplied by change in volume 10 centimeter cube, and 1 centimeter cube is 10 to the power minus 6. Now just simplify this part, you will get change in internal energy. Harsh, is it clear?
Yes, sir.
Just write it down.
Yes, sir.
Yes, Harsh.
So what's the answer?
I think it will be 32 point something.
Because I'm getting 31.8.
Okay, let me just solve it. If you remove this decimal, then it will be 10, 0 and 0 will cancel out. So just multiply 8 into 2, 16, and 8 into
16.
4, 32. So it will be 33.6 is equals to du we have to calculate. And if you simplify it, you'll get just 1.
1.
So du will be equals to 33.6 minus 1. So it will be
Minus.
just 32.62.
Okay, sir. Calculation. Done, sir.
Next question is, okay, so next question is, on the basis of relation between Cp and Cv, you'll be asked, to define Cp and Cv.
Cv.
Next question will be why Cp is greater than Cv. And third question will be derive relation in between these two parts. So we may define Cp and Cv as Cp is molar specific heat at constant pressure and Cv is molar specific heat at constant volume.
Constant volume.
So you may define it like as the amount of heat is required to change the temperature of 1 mole gas by 1 Kelvin at fixed pressure or at constant pressure. So it will be Cp. And similarly, this entire thing will be done at constant volume. So it will be Cv. Is it clear?
Yes, sir.
Next question is why Cp is greater than Cv? Let me define you this part. Suppose first we have at constant volume and second we have at constant pressure. At constant volume, since work done will be 0, change in volume is 0, so work done will be 0. So according to first law, dq is equals to du plus dw. So dw will be 0. So amount of heat supplied to the system is utilized only in changing internal energy in this part. Is it clear?
Yes, sir.
Suppose if you have supplied 10 joule of energy to this particular system. So this entire 10 joule will convert it into changing internal energy of a gas. Is it clear?
Yes, sir.
But in second part, at constant pressure, according to first law, dq is equals to du plus dw. If you supply 10 joule of energy to this part, some amount will be utilized in changing internal energy and some heat will be utilized in changing work done. So we can say, let's say 7 joule will be to change internal energy and 3 joule to do some work. Now, suppose if you have to take this internal energy to be 10 joule. So you must have to increase the amount of supply of heat to this particular system slightly more. Let's say it will be around 14, 15 joule. Let's say 15 joule. So only in this part, it will become 10 joule and it will become 5 joule. Is it clear?
Yes, sir.
So if you have to get same amount of internal energy in both these two different processes, just compare the amount of heat supplied, which is more at constant pressure, at constant volume.
Constant pressures.
That's why Cp is greater than Cv. So you'll be
Okay.
asked why so? So you'll say at constant volume, the amount of heat being supplied to the system is utilized only in changing internal energy. But at constant pressure, the amount of heat being supplied to the system is utilized in changing internal energy as well as doing some work. So if you have to get same amount of internal energy in this process, you must have to apply or supply some extra amount of heat in this particular part. That's why Cp is greater than Cv. Is it clear?
Yes, sir.
You may just write it down and I'm defining this entire process.
Done, sir.
Okay.
Sir, sir, just a minute. Some issues with the lab. 1 minute.
Okay.
So there are some issues with the laptop.
Okay. So we may define this process as, you will say, at constant volume, amount of heat
Supplied
to the system
is only used as internal energy.
is utilized in changing
Internal
energy only. But at constant pressure,
amount of heat supplied to the system is
amount of heat supplied to the system
is utilized in changing internal energy and doing some other.
As well as doing work.
Yes, sir.
So to get same amount of internal energy, at constant pressure, more amount of heat is required. Hence, Cp is greater than Cv. Next, let me define the mathematical part of this. First, write it down.
Done.
So we may derive this particular result as, you'll say, at constant volume, since delta V is 0, so amount of work done in this process will be 0. So using first law, you can say, using first law of thermodynamics, dq is equals to du plus dw, and since dw is 0, so du is equals to dq. Heat supplied is equals to n times c into dt, and c in this part is at constant volume, so it will be cv. Let's say this is equation first. Is it clear?
Yes, sir.
And at constant pressure, delta P is equals to 0. So using first law, dq is equals to du plus dw. dq is nc dt, amount of heat supplied at constant pressure, so it will be Cp. du you have calculated using first equation, so you may just put it in this part. Work done is P times dV. I've just used expression of du from equation first in this part. Now we have to transform this PdV in term of temperature. So we may write as PV is equals to nRT, ideal gas equation. So if we differentiate with respect to temperature, differentiating with respect to temperature. So differentiation of first part, that is pressure, multiplied by volume, plus differentiation of volume multiplied by pressure is equals to nr, and T being constant, so its differentiation will be just 1. Is it clear?
Yes, sir.
Now in this process, we have constant pressure. So differentiation of any constant part will be 0. Is it clear?
Yes, sir.
So this entire term will be 0. This entire thing will be 0 in this part since pressure is constant. Just 1 minute. Instead of doing this whole part, you may write like this. P is constant, keep it outside. Differentiation of volume dV by dt is equals to nr, and differentiation of temperature will be just 1. So move this delta dt to right side. So you'll get PdV is equals to nr dt. Now just substitute this value in place of PdV in this equation. So n times Cv into dt is equals to n times Cv into dt, and PdV is equals to nr dt. Now take out n dt as common. So n dt times Cp is equals to n dt times Cv plus R. So n dt will cancel out. So you'll get Cp is equals to Cv plus R. This is called Mayer's relation. Harsh, is it clear?
Yes, yes, sir. Yes, sir.
Just write it down.
Done, sir.
Get out up to this part.
No, sir. So after this topic chapter is finished, right?
I've defined one more topic, that is statement of Kelvin and Planck's statement,
Oh
which
yes,
is
yes,
second law of
yes, sir.
thermodynamics.
Yeah, yes, sir. And after this, like, what are you doing? Kinetic theory of gases.
Yeah.
Okay.
Should I define you some theoretical question related to this part? This
Yes,
entire
sir.
different.
Yes, sir.
There will be some theoretical question like why on long drive pressure inside tire of vehicle increases, or this increase of pressure will leads to bursting of tire, or you'll say tire of vehicle.
Sir, I have read this question, but I don't remember the answer.
Got burst. Yes, Harsh?
Sir, I have read this, sir, but I don't remember the answer properly.
Okay, no problem. Let me define you. Mechanism
It was
behind
due
it.
to temperature. Wait, it was due to temperature.
Yeah.
Yeah, it was due to
Suppose,
temperature.
yeah, it is related somehow with temperature. You will say, if you fill air in tire of a vehicle, its volume will be constant at that particular instant.
Yes.
Is it clear?
Yes.
Next, on running over track, there will be friction between tire and road.
Yes.
Is it clear?
Yes.
This friction will generate some heat, and heat will cause us to increase the temperature of gas inside tire. Is it clear?
Yes, sir.
Now, due to increase in temperature inside, since volume is constant, so at constant volume, pressure and temperature is directly proportional to each other. That is for isocoric process.
Yes.
So increase of temperature will leads to increase in pressure.
Increase in pressure.
That's why pressure in tire, inside tire for
Increases.
long drive increases. And if it becomes so insufficient or significantly large, then tire get often burst on long drive. Is it clear?
Yes, sir.
So you'll say there is friction in between road and tire. So heat will generate in motion which will cause to increase the temperature of gas. And volume is constant. So pressure and temperature is directly proportional to each other. Hence, pressure increases. That's why tire often gets burst. Is it clear?
Yes, sir.
Next question will be, we may define two different processes, that is isothermal and adiabatic, on the basis of their rate of action. So one of the thing is quasi-static process. If a process carried out very slow, almost it tend to act as a rest, then it will be termed as isothermal process. It means delta T will be 0 in this part. And if a process is occurring very fast or quick action, then it is adiabatic. Delta Q is equals to 0. Is it clear?
Yes, sir.
So you will be asked, suppose on bursting tire, air will escape out from that part. So what would be the temperature of that escaping air with respect to surrounding air? Will it be cold or hot as compared to the temperature of surrounding? Similarly, if balloon got burst, what would be the temperature of air escaping out from the burst balloon with respect to temperature of surrounding? Which will be cold or hot?
It would be hot.
No.
No? Sir, how can it be cold?
Let me define you. Suppose this is balloon. So to blow it up, you must have to apply some external agency or work to blow it up. It means pressure inside this balloon will be greater as compared to pressure of outside. That's why we have to do some work to blow it up. Is it clear?
Yes, sir.
So we can say pressure is more as compared to outside. On bursting, it will come in contact with atmosphere.
Yes,
It
sir.
means on going from this part to this part, pressure will decrease or increase.
Pressure will decrease.
Good. And this bursting of balloon will be slow process or quick process?
Quick, sir.
Quick. So it will be isothermal or adiabatic?
Adiabatic.
Good. So for adiabatic process, pressure and temperature is directly proportional to each other. So if pressure decreases, so temperature of gas must decreases. Is it clear?
Yes, sir.
That's why ejecting air will be cold. Any doubt?
No, sir.
Just write it down to this part.
Yes, sir.
Yes, Harsh.
Yes, sir.
Any
Tell.
problem?
No, sir. Done, sir.
Okay. So last part you may explain as, since bursting of balloon is quick process, so it will be adiabatic. And pressure directly proportional to temperature. So decrease in pressure will tend to decrease in temperature. That's why ejecting air will be cold. So ejecting air or escaping air will be cold as compared to the normal temperature of air. You may just write it down.
Done, sir.
Now to define next to a statement, we have to first explain you heat engine. So let me define the basic part of heat engine, or just introductory part of heat engine. So first, what do you mean by heat engines? You will say it is an engine which convert heat energy into useful mechanical energy. Is it clear?
Yes, sir.
An engine which convert
Heat energy into useful mechanical energy.
heat energy into useful mechanical energy. It consists of three different segments. First is called source, or simply heat reservoir. Second is working tool, and third is sink. This is called source or heat reservoir, having temperature T1, from which it absorbs Q1 amount of heat. And by absorbing this much amount of heat, work is done on piston to expand or contract it, and some amount of heat is being ejected out into surrounding, which is called sink in this part, which having temperature T2. So related to this part, we may define its efficiency of working. Efficiency of working represented by eta. How much energy has converted into work done to the amount of energy absorbed by it. So it is work done divided by heat absorbed, that is Q1. Work done is 1 minus Q2. If you simplify it, you will get just Q2 divided by Q1. In terms of temperature, it will be T2 divided by T1. Now, from this part, you will be asked, suppose, how will this efficiency becomes 100% or 1? That is only 1. So this efficiency, it has to become 1. First thing will be T1 should be infinite, so that 1 by infinity becomes 0.
Zero.
And only in that case, efficiency of heat engine will be maximum, that is 100%, that is 1. And we can't increase the temperature of source up to infinite temperature. It will be not possible. Is it clear?
Yes, sir.
Second way is to convert this particular efficiency or make this particular efficiency to be 1 or 100% is T2 to become 0. So if T2, that is sink, if it becomes 0 Kelvin, then efficiency will become 100%. And again, at 0 Kelvin, that is absolute 0, there is no existence of any matter. So we can say it will also be not possible. So in general, we can say efficiency of heat engine can never equals to 1 or 100%. Is it clear?
Yes, sir.
So related to this part, we may define two different statements related to second law. First is
Kelvin's Planck's law.
Planck statement.
Planck's law, sorry, Planck's law.
It was not law, it is just a statement related to second law. And second is Clausius statement.
Clausius statement.
In first part, let's say this is source and this is sink. Working tool. This is first heat reservoir. So it absorbs Q1 amount of heat and complete conversion of heat into work done without any loss of energy into surrounding. This process will not be possible at all, because at this part, Q2 will be 0, and if Q2 becomes 0, efficiency of heat engine becomes 100%. And in previous part, I had explained you, efficiency of heat engine can never equals to unity or 100%. Is it clear?
Yes, sir.
In second part, according to Clausius statement, it absorbs Q2 from some lower temperature body and complete transfer of it towards higher temperature body without any need of external agency. So it will also not possible. So in this part, this is heat reservoir or a body which is at higher temperature, and this is some cold surrounding which is called sink. So in this part, we can say, or a statement related to this is, no process is possible whose sole result is absorption of heat and complete conversion into mechanical energy or work done. Work done or mechanical energy without any loss. In second part for clauses statement, we can say no process is possible whose sole result
is transfer of heat energy from colder object to hotter object.
good, whose sole result is absorption of heat from
colder
cold
object
body
to hotter body.
and transfer it to higher temperature body. So this will also be not possible. Is it clear?
Yes, sir.
So first you may write this part and then that part.
So can I scroll it down? Done, sir.
Okay. Next is, what do you mean by intensive and extensive property?
Yes, sir.
What do you mean by intensive and extensive property?
Intensive and extensive property.
Yeah.
Intensive and extensive. Sir, extensive depends on size of the system.
No, it will depend upon mass of the system.
Mass.
Yeah.
And intensive depends on the
Mass
Oh,
independent.
no, intensive is independent of the size of the system, and extensive depends on the mass of the system. Yes.
So intensive is mass independent and extensive is mass dependent.
Sir, it's mass.
Mass, shape, size.
Because
No, I think it will be mass. It will be
because
mass.
I guess in my book I wrote size.
No, it will be
And
mass
teacher
independent.
calculated. Yes.
Mass independent, and this is mass dependent.
Yes, sir. Mass independent, mass dependent.
Let me give you some example of these part. You will say pressure, density. In this part, you will say internal energy, volume, these terms. So this is all about this entire chapter, that is thermodynamics. Okay.
Okay, sir.
Anything more in this part?
No, sir. That's it in school that they did.
Okay.
Sir, just let me check 1 minute. Yes, sir, that's it.
So next we start with kinetic theory of gas.
Yes, sir.
Tell me the topic you did in school.
Sir, first gas law.
Gas law.
Gas
Okay.
law. In that Boyle's law, Charles law, Gay-Lussac's law, ideal gas equation, and then postulates of kinetic theory of gas, and then again ideal gas equation, Avogadro's hypothesis,
Okay, next.
and then so then this expression of for pressure exerted by gas is deleted.
Deleted?
It's not deleted, means it's not common exam for us.
Okay, then next.
Degree of freedom,
Then next.
and then specific heat capacity of solids.
Next.
Mean free pathway.
Okay, the last part.
Yeah, the last part. And some, sir, after expression for pressure exerted by solids, there is some part that I didn't write. So it's also there.
Okay. Since in this part, that is kinetic theory of gas, there is some relation between thermodynamics and kinetic theory of gas. It means laws, that is thermodynamical laws for different thermodynamical processes, same for either of these two chapters. So again, we may define according to ideal gas equation, PV is equals to nRT. First, if P is constant, that is called Charles' law. Next, if V is constant, that is called Gay-Lussac's law. And third, if T is constant, that is called Boyle's law. Then you have done a graph related to this part, or just only definition
Yes, a
related to
graph
this?
is there. Graph is there.
Okay.
Graph
So
for
only
all three.
So only PV graph or rest of it or different graph?
So for yes, sir, it's PV graph and
Okay.
P and P by P and 1 by V.
Okay.
And then for Charles law also it's the same. For Gay-Lussac's law it's P by P and T graph, like pressure and temperature. Yes.
So for first part, if you draw variation of gas, how will you define this particular Charles law? You will say, if a process is carried out at constant pressure, so volume and temperature will be directly proportional to each other. So let's say if you have to plot variation of graph, pressure versus volume. Since pressure is constant, so it will be a straight line since pressure is not changing. So it will give just a straight line like this. Is it clear?
Yes, sir.
So it must be changing from this point to this point. Next, in case of for isothermal, pressure versus volume, these two terms will be inversely proportional to each other. So graph will be a rectangular hyperbola like this. So let's say if we have two different curves related to some temperature T1 and some temperature T2 like this. So you will be asked which of these two temperature is more. So you will say if graph is away from origin, it will more as compared to the next part. So we can say T2 is greater than T1 in this part. Now suppose if you have to plot pressure versus 1 by V. Is the second graph? Harsh?
Yes, sir.
It is the second graph in this part.
Yes, sir.
So you may write according to ideal gas equation, or PV is equals to constant. So in this part, 1 upon V and pressure will be directly proportional to each other. You may write it like this: P is equals to nRT divided by V. So it will be nRT multiplied by 1 by V is equals to P. Is it clear?
Yes, sir.
So in this expression, P is directly proportional to 1 by V. So what will be the nature of graph for this part? It will be straight line.
Straight line.
Yeah. So it will be straight line like this. So greater the slope of this particular graph, it means greater will be temperature. So next, let me define you. First graph is from this point to this point. Second graph is from this point to this point. So greater the slope of this particular curve, it will have greater temperature as well. Let's say this is A and this is B. So temperature of B will be greater than temperature of A. Harsh, is it clear?
Yes, sir.
Next, in this part, since volume is constant, so if you plot pressure versus volume, so it will be a straight line parallel to opposite coordinate that will be along this direction. Similarly, if we plot pressure versus temperature, since at constant volume, pressure and temperature will be directly proportional to each other. So it will be a straight line like this. So if you have to check which of these two terms is more, let's say this is VA and VB. So according to ideal gas equation, PV is equals to nRT. So P divided by
Yes,
T
sir.
will be nR divided by P. It means slope of this particular curve will be inversely proportional to volume. So we can say greater the slope of this curve, it will have a smaller volume. It means VA is greater than VB for this part. Similarly, if you plot for the first part, volume versus temperature. So again, graph will be like this. It will be a straight line passing through origin. And again, in this part, greater the slope of curve, it will have smaller pressure. Let's say this is A and this is B. So pressure of A will be greater than pressure of B. Any doubt in this entire different part?
No, sir.
Okay, just write it down.
Yes, sir. Done, sir.
Next is Avogadro's law or Avogadro's hypothesis. According to ideal gas equation, PV is equals to nRT. Is it clear?
Yes, sir.
So you may write N, that is number of moles, as number of particles divided by Avogadro number is equals to P times V. Now in this part, we can say if pressure and temperature is same, then for equal volume of gas, number of particles will be same for all different gases. It means
States that
at constant pressure
and
and
temperature
temperature, equal volume
of
of
gas
all gases
have equal number of molecules.
contain equal number of particle, molecule, atom, particle, molecule, or atom. And that is equals to Avogadro number, that is 6.02 root 10 to the power 23. Is it clear?
Yes, sir.
So this is Avogadro's law. Just write it down.
Done, sir.
So these are different laws related to this part. Next is property of ideal gas. Next is property of ideal gas. First is, we can say ideal gas or the gas in which there is no interaction between particles. So first property is there is no interaction between particle of gas. Next is velocity of particle along each different coordinate axis will be same. Velocity of particle along each direction or coordinate will be same. That is velocity along x-axis, velocity along y-axis, and velocity along z-axis will be equal. Next is it acts as solid rigid sphere. It acts as solid rigid sphere. So it collides elastically with neighboring particle as well as wall of the container. So it makes elastic collision with neighboring particle or with wall of container. Is it clear?
Yes, sir.
So these are different properties related to ideal gas. Just write it down. On the basis of this assumption, we may derive pressure exerted by gas, but since it is deleted portion, so we'll continue with thermal kinetic energy.
Done, sir.
Okay, any doubt to this part?
No, sir.
So let's stop here for today. In next class, we'll start with thermal kinetic energy, that is kinetic energy related with temperature, then law of equipartition of energy, and then calculation of internal energy and specific heat.